Today, I will be talking about LEMNA. This is a joint work with my collaborator from Penn State and Virginia Tech. So I'm quite sure that you all know deep learning has been widely adopted in many, deep learning has been widely adopted in many applications. It's also becoming increasingly popular in cybersecurity. Yeah, we start from here as the example. This is a machine code, a sequence of machine code, which indicates the instruction that the computer executed. So using recurrent neural network, a specific type of network structure, we can identify the machine code that indicating the start of the function in this sequence. So the left side table here demonstrates that machine learning can establish better performance than state-of-art approaches. Although deep learning or machine learning method can achieve like very high accuracy, it still suffers from a lack of transparency issue. Because deep learning is a black box, we may have the following three concerns. First, user and designer are not able to establish trust to model behavior. Here is an example. Recent research has shown that a small perturbation on the original data sample can cause the model to make mistake. But because we cannot explain the model behavior, so we are not able to, we have limited clue of why this kind of adversarial sample phenomena exist. But even without perturbation, deep learning model can still make mistake on the legitimate sample. Because of the black box nature, we also cannot debug the deep learning system or diagnose the model mistake. Sometimes model may bias to certain parts due to the training data issue. According to a recent news, a machine learning-based criminal prediction system suffers from racial bias. It may cause innocent people get arrested. But according only to the model output, we are not able to find this kind of racial model bias during the testing process. Actually, of the aforementioned concerns are because of lacking of explanation. Here we first introduce what is a model explanation. So recall that when training a network, we just input the data or say image into the models. So model takes a bunch of pixels as input. So and then output a model decision. So here for explanation, we refer that the set of features that make a key contribution to the model output. We also take image recognition as the first example. Here, the model identifies a tag in the cat in this image. And the explanation is just a bunch of pixels or group of pixels that indicate this model result. So the explanation is the image on the right-hand side. For identifying binary function start, we take the same example I used before. The explanation is the heat map that indicating the feature importance. In this heat map, the red color means indicating the most important features. So in machine learning community, there are already some techniques try to derive explanation from the model, but not most of them are designed for convolutional-based vision applications. So they are not suitable for the security application because of the following two limitations. First, as I will show later, existing approach can only provide a coarse-grained explanation, which is fine for the application that require fuzzing or fast explanation, such as image recognition. But we all know that security applications have very low error tolerance. This means that existing technique cannot satisfy the high accuracy requirements for security application. The second limitation is that security application usually has sequential data, say a sequence of hacks I showed before. So this kind of data require a sequential model, say recurrent neural network. But existing approach are designed for convolutional network, so they cannot be directly plugged in and used in recurrent neural network. So in the next two slides, I will first use a state-of-art method as an example to demonstrate how to derive explanation, and then using this example, I will introduce in detail about these two limitations. First, given a well-trained neural network model, here I just draw the decision boundary as this. We want to explain the model decision at this point X. So we want to know why model take this image as a cat. So the key idea of this approach is that they want to locally approximate the decision boundary around this x point, and derive using a interpretable model, and then derive the explanation from this interpretable model. So to achieve this goal, first we need to do some we need to generate some new samples. So we perturb the feature on the original sample and generate some synthetic data. So and then we input this crafted data into the model and get the model output. Using the data, generated data and the model output, we can fit a simple model, say linear regression, to approximate this local decision boundary. And then we need to generate an explanation from this simple linear model. The way we do this is that we rank the regression coefficient beta 1, beta 2 to beta n. So we find the features that attach to the highest highest coefficients. Then we can find the important feature. So in this image, just these three parts contribute to the model output. So using this example, now I will introduce in detail why these two limitations exist. First, the limitation is that the existing approach cannot provide an accurate explanation. Recall that in last slides, we use a linear function to approximate the local decision boundary. But for neural network, what we get is usually a very complex or nonlinear decision boundary. So if we force linear approximation, in this case, we will cause errors. So here is an example. We linearly approximate this very nonlinear decision boundary. What we get is a inaccurate approximation. This will result in an inaccurate explanation. So second, recall that security applications usually have sequential data, which means that there are certain kind of feature dependency within the input data. But most of the existing approach assume that the input features are independent from each other. So they are not able to model this kind of feature dependency. So in this example, if we take feature independently, what we get is a bunch of individual features. So there is little correlation between the selected feature. So this will also cause errors. So to address the limitation we mentioned earlier, we propose a new explanation technique. To be specific, we propose LEMNA, which is a local explanation technique for security application. In the following, I will introduce how LEMNA achieve these two goals. First, providing accurate explanation. To achieve this goal, instead of using simple linear approximation, we use a mixture regression model to do the approximation. A mixture regression model is just a combination of multiple linear regressions. And this kind of model has been proved that it can approximate arbitrary decision boundary, which means that by theory, the mixture model can give us a better approximation than linear regression. Here is a inaccurate case using linear approximation. But if we approximate this decision boundary with a mixture regression model, so here the mixture regression is just a combination of multiple linear regressions. And we identify the best component where the original data sample here, the dot here, lies in. What we get is, you can say that we can better recover the decision boundary. So since we have a more accurate approximation, what we get is a more accurate explanation. So second, so we want to customize our method to recurrent network. More specifically, we want to model in the feature dependence. So to do this, we integrate a special regulation term into the mixture model, which is called fields lasso. The fields lasso is designed to model the feature dependence I mentioned before. So with fields lasso, instead of select individual features, we can select a bunch of features or group of features as the important feature. So here is the example of individual features. But with fields lasso, what we get is linear regression as this. Since fields lasso can force the adjacent feature to have some equal weight, so the regression we get here is something like this. So if we do feature selection based on this form, what we get is a group of correlated features. So this will also lead to a more accurate explanation. So then I will demonstrate how to derive an explanation with our technique. say there is a decision boundary and we want to explain the result at point X. What we do first is that we also need to generate some artificial data with a method, the same method as I mentioned before. But instead of fitting a linear regression here, we fit a model that we proposed, which is a mixture regression model with the Fields lasso regulation term. After doing the model fitting, we need to find the best component here. Well, we extract this component and generating the explanation based on this mixture component. The way we do this is also we do the feature ranking and find the important feature that attach to the highest regression coefficient. So in this way, what we get is a more accurate explanation. But we need to do the evaluation about the explanation accuracy, right? So in this paper, we actually did two groups of experiment. First, but due to time limit, here I only demonstrate a result on identifying binary function start. The way we evaluate our explanation accuracy is that we design 3 groups of end-to-end fidelity tests. The key idea of this fidelity test is that if we select the right feature, perturbing this feature will cause deep learning model to make different mistake. Here, I use a feature deduction test to demonstrate our fidelity test. Given a test example and the important feature that LEMNA selected, we generate a artificial sample by nullifying the important feature that LEMNA identified. This is called deduction sample. Intuition suggests that if we input this deduction sample into a model can no longer identify this image as a cat because we already nullify the important parts of the images. And then we generate a deduction sample for each sample in a testing site. Well, our expectation is that we expect the the classification accuracy of deep learning will drop to a certain degree. Here is a result. From this result, we can show that LEMNA established the highest accuracy drop, which means that LEMNA can establish the most accurate explanation. But why LEMNA is useful? So here I will show how we can use LEMNA to help us first build trust of the target model and then troubleshooting and patching the model errors. To build trust of the target deep learning model, first we want to make sure that deep learning model can capture the well-known heuristic. It's that what's learned by deep learning model is actually makes sense to human. So here is an example how LEMNA can help us achieve this goal. In this example, deep learning model identified 55 as the function start. What LEMNA gave us is this heat map indicating the feature importance. Within this bunch of hacks, these 3 hacks are marked as the most important features. If we do disassembling, what we get is this instruction. This is actually a well-used heuristic by binary analysts. So this case demonstrates that LEMNA can help us check whether the model captured the well-known heuristic, and this model indeed captured the well-known heuristic. But second, we know that deep learning can achieve very high accuracy, like 99.9. With beyond this well-known heuristic, the model, we assume that model need to discover some new heuristic that cannot be exhaustively summarized by human. In this example, here is an example. In this example, LEMNA identified this bunch of features as the most important feature, and it refers to this instruction. Within these 2 instructions, this sub-instruction usually used in the at the start of a function to do a stack preparation. Despite this pattern seldom happened in the binary codes, but it actually makes sense to the binary analyst. So this means that the model indeed discovered some new heuristic. From the formal analysis, we can make a conclusion that this deep learning model we learned can actually learn the right knowledge, so we can trust this deep learning model. Second, we also want want to know that why model make mistake. To be specific, we want to know the reason for false negative and false positive. Take false positive for example. The LEMNA tell us the reason for false positive is that indicators for function start sometimes appear in the middle of a function. In this example, the deep learning model wrongly takes this h3 as the function start. LEMNA tell us, okay, this branch of hex is the important feature. What we get is this instruction. So here the return instruction usually happens at the end of a function. So this indicates that the next instruction following the return is highly probability to be classified as a function start. But in this case, this return function accidentally happened in the middle of a function. This return instruction accidentally happened in the middle of a function. So the model wrongly takes this h3, the following instruction as a function start. So start from the error. We also try to patch the error using some patching method we designed. Here is the workflow of how we patch a specific error. Given an error and given a model error, we first use LEMNA to pinpoint the important feature that lead to these errors. We call these error features. And then we synthesize data based on this error features. Is that we replace this error feature with some random numbers. The intuition behind this is that if we replace this error feature and use to synthesize some new data, and then if we train the new data, train the model with this new data, the model probably may not able to learn this error feature or error patterns. So the model may not make this kind of mistake. So then we train the argument this data into our training set and retrain the target model. Here the results show that we can indeed reduce both false positive and false negative. To conclude my talk, explanation is very important, especially for security application. As we shown in this paper, leveraging mixture regression model and fields lasso, we can derive high accurate explanation for the application we studied. But this is just the beginning. So there's still an emerging need for model explanation in other deep learning-based security application. I'll give you one example. In this paper, we designed our LEMNA based only on one single model architecture, which is recurrent network. But there are already some published paper in this field that leverage a hybrid model, say the combination of recurrent network and convolution network to solve certain security problem. So in the future, we will explore whether our LEMNA can be extended to this kind of hybrid models. Okay. Thanks for the attention. I'm ready to take some questions.
Question? Question from the audience? But I have one. Can you go back to the slide where you compare the results and the explanation?
Yeah.
So you were comparing LEMNA with other methods to essentially change. Did you test it against? So, like, I mean, if I understand correctly, the idea here is to remove some of the pixels from the image and see if you remove the most meaningful one for the classifier, right? And that's exactly the purpose of when you generate adversarial samples, you do the same, right? So you manipulate the most relevant pixels to some extent.
Yeah.
Did you test that as a comparison method here? Trying to delete the pixels which are suggested by some algorithms to generate adversarial samples.
I'd also sample. I didn't do that, but I just didn't do that. But I did, before doing this work, I did some other work too. I also wondering this question actually. So in some case, this is not the truth. Is that this is very interesting actually. So the explanation method tell you the different feature importance than the adversarial method. Is that when you're generating the adversarial sample, you may identify some different feature than the explanation method. Yeah. Also, it's that when you're generating adversarial sample, sometimes you may use you just compute the partial derivative, that is that gradient, calculate the gradient, and then map back into the input. Yeah. But I didn't cover in my talk, but in our paper we discussed there exists a type of explanation method that uses a similar approach to do the explanation, that they backpropagate from output all the way back to the input and identify some important feature. So I compared our method with those kind of approach, and it shows that our method can give you better, like more accurate explanation. Yeah.
Okay, so can you talk a little bit more about how can LEMNA be applied to other scenarios, like other security applications, other than the example you just talked about?
Yes, if the other security application using simple, as I mentioned before, if the other application using a single model architecture, like single recurrent network or single feed-forward network, the LEMNA can just directly apply to them. But if the model is like hybrid model, we need to do some future work to extend LEMNA to those kind of models.
Okay, thank you for your answer.
Thanks.